10 cars on top of this table. Why the hell doesn't this table break? You think these legs can hold up 10 cars? Not a chance. How come the table doesn't break? More importantly, how come you don't go, pfft? Oh, sort of. You're really close. What's the pressure on the air underneath the table? The same thing. So is the table getting compressed? Yes, but the table can do that. Right? In terms of pounds per square inch, one atmosphere is 14.7 pounds per square inch, or 14.6. I don't remember. I think it's 14.7. All right? That means for every inch on your skin, you have almost 15 pounds being pushed down. But guess what? You have almost 15 pounds of pressure, fluid pressure inside pushing out on your skin. All right? So, you're a free diver. You don't know what a free diver is? That means they don't use scuba tanks. Okay? They just dive down. All right? When they dive down, what happens to their body? It gets smaller. Because the pressure increases and their volume goes down. But for the guy who uses a scuba tank, what's happening? Well, he's breathing air pressure at the same pressure that's on the outside, that the water is. So he's breathing air at a higher pressure. How come he doesn't blow up? Because the pressure on the water is the same as that, right? So he keeps breathing air at this higher pressure. His body fills up so that his skin stays at the same volume. All right, what's the problem that happens then to a scuba diver? Because he's down underwater, he's been at 100 feet for a long time. Okay, he has to decompress. Why? Correct. When you take what is 80% of what we breathe? Nitrogen. All right? When I start to compress nitrogen, it is more readily accepted into your bloodstream. I mean, can you put gas in a liquid? Yes. What's a common gas in a liquid? Yeah, y'all drink soda pop? Or whatever version name you want to use for that. For my wife, she is from Colorado and they drink Coke. That means that's Dr. Pepper, Sprite, any version, but they're all called Cokes. All right? In the East Coast, it's a soda. All right? But there's carbon dioxide in the water. Well, when you increase the pressure above 1 standard atmospheric pressure, your blood can absorb nitrogen. But when you then release the pressure back to an atmosphere, that nitrogen goes from inside, just like when you open up the can. Right? What happens when you open up a can of Coke? Does all of it go out? No, but some of it goes from being dissolved in a liquid to being a gas bubble. And that nitrogen happens in your bloodstream. And you can die. Not a good thing. Just making sure. I want you to know, I think dying is not a good thing. Lots of things can go towards dying, but we want to try to avoid those. All right? So, but we're still dealing with the whole concept of atmosphere. All right? The fact that there's 10 cars being pushed down on this table, there are 10 cars being pushed up on this table as well. That's why the table doesn't break. All right? So, now let's think about your tires for a second. Do you have to fill your tires with air? Okay, so if you have a flat, goes and now the rim of the tire is sitting down on the ground and all of those things. Right? What's the pressure inside your tire? It's 1 atmosphere. Think about it. If there was 0 air inside your tire, wouldn't your whole tire be squished in? Because and it's not that it gets squished in, that it gets sucked in, it's the fact that the air pressure pushes it in. 14 pounds per square inch, that's a lot. And it'll flatten that tire, nothing, without any problem at all. So there's a difference between gauge pressure and absolute pressure. If your tire's flat, it has a gauge pressure of 0. It doesn't mean there's nothing in it. You hear the difference? All right. So these are some of the things that we want to be able to talk about. And whoops, come on. All right. Pressure and fluids, and we'll get more back to, this, to the gauge pressures and all of those things. We have some considerations. We are dealing, most of this is going to be physics land, and until we get to Bernoulli's equation, we have static fluids. That means the fluids aren't moving. With Torricelli or Bernoulli's, then we have moving water and moving fluids, and we'll deal something else at that point. All right? But if I have a column of water, the farther down into the water I get, the higher the pressure is, because that level of water is what's holding all the water above it. All right? And what's going to happen is that the difference between those pressures, so I have whatever P1 is, I have that, whatever P2 is, but doesn't P2 have to hold the pressure of P1 plus all of that? And that's what we're saying. The P2 is equal to the pressure at 1 plus, yes, you can't see past your hat, I'm sorry. All right, so pressure due to a column of fluid, this one you need. Pressure due to a column of fluid is rho g h. That is the density times the acceleration due to the planet that you're on, which virtually for all of our problems will be 9.8. But we might be on Mars, okay? And then g is going to be 3.4. All right, times whatever the height is. Yeah?
Why is G
3.4 because that's G on Mars.
Oh, okay.
G is, when we do that lowercase g, almost always we will use 9.8.
Okay.
But we use 9.8 because we're assuming the problem occurs on Earth.
Okay.
Right? If it doesn't occur on Earth, then G is not 9.8. G is the actual field of gravity on the surface of the planet. For Earth, it's 9.8. Yes, ma'am?
Never mind. I didn't see that other side of the diagram, and I was going to ask which height of
Because we are discounting, well, wouldn't P1? P1 would be rho G this H. Right? And so it was just doing then the difference between the two. But pressure, the pressure in a column of fluid is due to its density times gravity times the acceleration of gravity times the height. All right, so bigger depth, bigger pressure, all of those things. All right. What is pressure not going to depend on? Well, how about this? If I have, okay, I have here, and I'm able to measure the pressure, and I come out like this, right, and this is all full of water, and I have one here, like that, and that's all full of water, and I'm assuming those are at the same height. At the bottom, which one has a greater pressure?
The one on the left.
This one has a greater pressure?
One on the right.
This one has a greater pressure? They're equal. Their heights are the same. If I have them filled with the same fluid on the same planet, the heights are the same, rho GH was the same for each of them, then the pressure at the bottom is the same for each of them. It doesn't matter how it gets stacked up. And you're going, but how can that be? Isn't there more water up here? Yes, but look, isn't this pushing that way? So it takes care of all the water that's over there. The pressure here is only due to that. And you're going, okay, well then how come the pressure here isn't only due to that? Well, what's keeping the water there? Isn't this pushing that way? Isn't there a component of that normal force that's being pressed onto the water? Isn't there a component of that that's going down? And when I add that component plus that height, that rho GH, I get the total pressure. Because think about it, that if I drilled a little hole here, what would happen? Wouldn't this go out the hole? Because there's pressure. All right? And pressure is only rho GH. The shape does not matter. That makes sense for everybody? All right? And I know I'm loud and obnoxious sometimes, but as I go through these, that's why I want to do the talking. Because I want to make sure that you understand what's happening and what are the important parts and what it is that you're looking for.
Oh, you're in the meeting. Let me get it out. Okay.
Okay. Gauge pressure and absolute pressure. A gauge pressure. And I love the way they say it, it's just measuring a difference. And what are they measuring the difference between usually? And whatever it is you're measuring. Right. It's the outside atmosphere and whatever you're measuring. So if you have a, oh no, my mind just went blank. Blood pressure cuff. But they're called a sphygmomanometer. There you go. If you have a sphygmomanometer, what's it measuring? It's actually measuring, right, your systolic and your diastolic pressure. All right? One's a high one, one's a low one, and I never remember which one's which. But
Diastolic is the high one and systolic is the lower one.
so diastolic's the high one, right? That's when your heart beats, it compresses. What's the pressure that it compresses the fluids out at? That's your high pressure. What's the low pressure?
When it relaxes.
When it releases.
When it relaxes, what's the minimum pressure it has to pump at? Your low pressure is what are in your arteries, basically your arteries and your veins all the time. Okay, if you have high blood pressure, either one of those numbers can be raised. Can the lower one ever be higher than the higher one? No, you all do follow that, yes? I know it sounds like a dumb question, but that's a question that people get asked. I mean, doctors get asked, all right? What are the dangers of the high pressure of either one? Because they are two different dangers. The which one?
It's more pressure on the walls of the artery.
It is, but what's the biggest danger of having too high a high pressure? What's your biggest danger? Not your heart. Your head. Because it is the pressure on the arteries. If your arteries or veins fail because the high pressure just blows them out, you have an aneurysm, you have a stroke. Okay? That's what happens with too high a blood pressure. When your low number is too high, that means your heart's doing too much work. When the low number is too high, it has to be able to, just to get the blood to go, it's got to push really, really hard. Y'all follow? Okay? The concept of gauge pressure, the concept of pressure, the concept of this, if you're going to be a doctor or a nurse, I personally really, really want you to understand that. All right? It has value. Now, personally, I think all of physics has value, so I know I'm biased. You don't need to tell me that part. I already know. So, gauge pressure, the difference between that and atmosphere. That means absolute pressure is going to be gauge pressure plus 1. It's whatever your gauge pressure is plus 1 atmosphere, and you win. All right, but do remember it's 1 atmosphere. Don't just add 1. If your pressure you're measuring is in pounds per square inch, you need to add 14.7. If you're measuring in pascals, you need to add 101.3 kilopascals, or 1.013 times 10 to the 5th pascals. Make sure you get the number. Yes, sir.
So that the gauge pressure is like 1 atmosphere pressure plus the absolute pressure?
No, absolute is 1 atmosphere plus gauge.
Oh, okay.
If you'd put a minus in there, it would have worked. Right? So absolute is gauge plus 1 atmosphere, or the change is the difference between, or all of those things. Different types of pressure gauges. So why do they read 1 atmosphere as 760 torr, 760 millimeters of mercury?